Hello students. So in the last class we were discussing about the D and F block elements. So we have discussed about the main chemical properties of the D and F block elements. So today we will be discussing about the lanthanoids, that is, which is coming under the inner transition elements. I hope you remember about the inner transition elements. What are inner transition elements? So when you look at the periodic table, those two sets of rows which is placed at the bottom level, that is, which is placed separately from the periodic table, they are known as the inner transition elements. So today in this video we are going to study about the inner transition elements. Actually there are two categories, there are lanthanoids and actinoids are present as the inner transition elements, but recently because of the CBSE updation about the syllabus, they have removed the actinoids from our syllabus. So today we will be studying only about the lanthanoids, and they have removed the chemical properties of the lanthanoids also. Okay, so only what is left under the inner transition elements is the lanthanoids. What are lanthanoids? What are their common electronic configuration, their oxidation states, and also about the lanthanoid contraction and its consequences also. It's a small topic. Okay, so we can watch it, and at the end of this video I have given the repeatedly asked board examinations questions also. See it, I have given the description also, the questions, their answers are also I have given, and at end of this video I have given the answer key also. So I want you to note it down in your notebooks. Okay, so I need you to write everything, that is all the previously asked questions in your notebook, but you have to study it also. Okay, so let us watch the today's video.
So in this session we are going to study about the inner transition elements. What are inner transition elements? You know that those elements which are in between that of the S block and P block, we call it as a transition elements, right? So at the bottom of this periodic table you can see two rows of elements is placed separately, right? So those two rows of elements which is placed separately, we call them as the inner transition elements. Okay, so what are inner transition elements? So inner transition elements are those elements in which their last electron is entering into the F orbital. Okay, so those elements in which their last electrons, the valence electrons, if they are entering into the F orbital, we call them as the inner transition elements. Okay, so inner transition elements are of two types. We have lanthanoids and actinoids also. Okay, lanthanoids and actinoids. So what are lanthanoids and actinoids is that, so lanthanoids are those elements in which their 4f subshell or a 4f orbital is getting filled. Okay, if the last electron is entering into the 4f orbital, we call them as the lanthanoids, and if it is entering into the 5f orbital, then we call them as the actinoids. Okay, so if electrons are filling 4f orbital, we call them as the lanthanoids, and if they are filling 5f orbital, then we call them as the actinoids. Okay, so in this session we are going to study about the lanthanoids only, because you know that our CBSE, as I already told you, the actinoids, this topic has been removed from our syllabus. The lanthanoids also, we are not studying any of the chemical properties. We are just going to study about their electronic configuration, their oxidation states, and the atomic and the ionic radii only. So these three points only. Now look at the lanthanoids. What are lanthanoids? As I told you, if the electrons are entering into the 4f subshell, then we call them as the lanthanoids. Okay, so lanthanoids are those elements which is coming after the lanthanum. After the lanthanum, we can see that there are 14 elements. So the 14 elements which are following lanthanum in the periodic table, and it has a property similar to that of the lanthanum. They are known as the lanthanoids. Okay, they all are metals. They are normally silvery type of metals and are having very low tensile strength and all, and they are very good conductors of heat and electricity also. Okay, so the 14 elements which are following the lanthanum, we call them as the lanthanoids. Okay, now look at their electronic configuration. Now we can look at their electronic configuration. What is the general electronic configuration of the lanthanoids? We know that 4f subshell is getting filled. So it's 4f 0 to, not the 0. We cannot say that if it is 0, then it won't be a lanthanoid. So 4f 1 to 14. Then 5d 0 to 1. Then 6s 2. Okay, so this is the valence shell. So the valence shell, this is the next shell, then this is the penultimate shell. So the third shell we call it as the penultimate shell. Okay, okay, so the this shell, this last shell, this shell we call it as the valence shell. Okay, this shell we call it as the penultimate shell, and this shell we call it as the anti-penultimate shell. Okay, so if the electrons are entering into the anti-penultimate 4f subshell, then we call them as the lanthanoids. Now we can look at the electronic configuration of all the elements. First you can look at each of these elements. You can look at that. Consequently, what is happening? The number of electrons present in the 4f subshell is getting increased, right? 4f1, 4f3, 4f4, like that it is increasing till it reaches the 4f14. So electrons are entering into the anti-penultimate 4f orbital. Then we are calling them as the lanthanoids. Okay, now it's about the electronic configuration. The common oxidation state, the most common oxidation state that is exhibited by the lanthanoids is +3. So lanthanoids are exhibiting a most common and the most stable oxidation state is +3, because most of the elements will be having a half filled or completely filled orbitals will be forming if they are in the +3 oxidation state. Okay, there are elements which is showing +2 or +4 oxidation state are also there. +2 and +4 oxidation states are also exhibited by certain metals, but the most common and the most stable oxidation state of the lanthanoids is the +3, because most of the elements are forming half filled or the completely filled orbitals if they are having the +3 oxidation state. Okay, so that's about the oxidation state. The next thing is that's the most important one. When we talk about the atomic radius, of the lanthanoids, we can see that when we go down, that is when we go from lanthanum to the lutetium, you can see that the atomic radius is getting decreased. Okay, the atomic radius decreases when we go from lanthanum to lutetium. That is when we compare to the atomic sizes, lanthanum will be the most largest one and lutetium will be the smallest one. Okay, what is the reason for that decrease in the atomic radius is that so when we go down, the atomic size is getting decreased. This gradual decrease in the atomic radius is because that, so when you look at the electronic configuration of the lanthanoids, you can see that the electrons are entering into the f orbital. Right, electrons are entering into the f orbital. So when we look at a nucleus, so this is a nucleus and the electron, suppose this is the anti-penultimate for f subshell. Okay, so electrons are entering into the f subshell. This is our penultimate shell and this is our anti-penultimate shell. Okay, so when we go from lanthanum to lutetium, its nuclear charge is increasing, right? Its nuclear charge is getting increased. That means number of protons present is getting increased, and the electrons, then if the atomic number is increasing, just like the protons, just like the increase in nuclear charge, electrons are also increasing, right? The number of electrons are also increasing. This number of electrons are increasing in the f orbital, right? If it is lanthanol, it will be 4f itself, right? Electrons are coming into the 4f orbital. This f orbital has a peculiarities that we have already studied in the case of d orbital. They are very poor in shielding effect. They are very poor in shielding effect. So they are very poor in shielding the outer electrons from the attraction of the nucleus. So the power of the nuclear charge is getting increased and the screening effect is getting decreased. So what will happen? The nucleus can attract the valence shell electron with a much force. So it will result in the decrease in the atomic radius. Okay, that gradual decrease in the atomic radius of the lanthanoids, we call them as the lanthanoid contraction. We call them as the lanthanoid contraction. Lanthanoid contraction is very important. So what is the reason for that is, when we go from lanthanum to lutetium, its nuclear charges increases, electrons are entering into the 4f orbital. F orbitals are very poor in their shielding effect, hence the nucleus will attract the valence shell electron with a much force, resulting in the decrease in the atomic radius. Okay, so that is the reason for the lanthanoid contraction. So the regular decrease in the atomic radius, we call them as the lanthanoid contraction. Okay, so the attraction of the nucleus for the electrons in the outermost shell increases as the atomic number of the lanthanoid increases, and what will happen? It will result in the decrease in the atomic radius. Okay, now what are the consequences of these lanthanoid contraction? Because of the lanthanoid contraction, what all things are getting happened? Okay, so what are the consequences of lanthanoid contraction? Consequences of lanthanoid contraction. What are the main consequences of lanthanoid contraction? So the lanthanoid contraction can result in mainly three effects. The first one is that, as we discussed in the transition elements, some of you have asked me the doubt regarding this, and I replied you that I will explain it when we are taking lanthanoid contraction. That is similarity of the second and third transition series. Okay, that is one of the consequences of the lanthanoid contraction. Because of the lanthanoid contraction means when we move across, what will happen is atomic radius is getting decreased, gradual decrease is there. So because of that, what will happen is second transition series and the third transition series, they will have a similarity in their atomic radius. Their atomic radius is almost similar, because in between the lanthanoids, they are experiencing a lanthanoid contraction. Okay, and the second consequences is the separation of lanthanoids. Separation of lanthanoids become very difficult. Okay, it become very difficult. Why is it so? Because they are having almost, there is a regular decrease in the lanthanoids, and that decrease is very small also. Since the change in the atomic radius of the lanthanoids is very small, what will happen? Their chemical properties are also become similar. Okay, so when their chemical properties are becoming similar, what will happen? They are having the same chemical properties, so it will result in the separation of the lanthanoids as a difficult one. Okay, so it is difficult to separate the lanthanoids because they are having similar atomic radii, so they are having similar chemical properties also. Okay, and the third one is there is only a slight difference in their atomic radii, right? And the last consequence is that variation in basic strength of hydroxides. what will happen there? Basically, we know that metal oxides are no basic in nature. So when we look at their hydroxide, that is metal OH form, right? The inner transition element, the lanthanose, and to that into which an OH group is getting attached. So the lanthanide contraction, because of the lanthanide contraction, what will happen means the ion size is getting decreased, right? Ion size will get decreased. So it will result in the increase in the covalent character of MOH bond. So this OM, since the ions present in the M in the ionic form, their size is getting decreased. Since the size of the M ions is getting decreased, so what will happen? So this covalent character, the bond, there's increase in the covalent character in the MOH bond. So what will happen means the OH, this cannot be released easily. So OH ions cannot be easily released. If the OH minus ions is not getting released easily, means their basic strength is getting decreased, right? So that is how it is varying. So when we go from lanthanum to lutetium, its basic strength is getting decreased because the due to the lanthanide contraction, size of the M ions is getting decreased, so their covalent character will get increased because its size is getting decreased, right? So its covalent character is getting increasing. So OH minus, we cannot release the OH minus ions easily. Okay, so it will result in the decrease in the basic strength of hydroxides. Okay.
So let us discuss some questions that are frequently asked for your board examinations. So some questions are repeatedly asking. So I choose only those questions which are repeatedly asking. So at the end of this video, I have given the answer key also. So I want you to copy it down in your notebook and study it also. So let us discuss the first question. Zinc salts are white while copper ion salts are colored. Zn2 plus salts are white while Cu2 plus salts are colored. What is the reason for it? The reason is that zinc ions have completely filled d subshell, means they have no unpaired electron. So what will happen here? Zinc ions are white in nature. Okay, so they don't have unpaired electron, they have completely filled d subshell. So d-d transition won't takes place over here. Next question. Why do transition elements show variable oxidation state? The answer is ns orbital and n-1d electrons of the transition metal, both the electrons from both the orbitals will take part in the bond formation. So it is resulting in the variable oxidation state, because now when ns electron take part in the bonding, they exhibit a lower oxidation state because they can contain only 2 electrons, right? But when n-1d electrons are take part in the bond formation along with the ns electron, they exhibit higher oxidation states. Okay, next is transition elements are much harder than the alkali metals. Why? Transition metals are much harder than the alkali metals. Why? Okay, so the answer is that transition elements involved in the more number of electrons from n-1d subshell in addition to ns subshell in the metallic bonding. You know that in the alkali metals they are involving only ns electrons. So here more number of electrons are there, so they are more harder. Next question. Which of the following cations are colored in aqueous solutions and why? They have given the ions, then they have given the atomic numbers also. What you have to do is you have to write their electronic configuration. You have to write their electronic configuration and check which one of these ions have partially filled the d orbitals. Only the partially filled d orbitals can undergo
DD transition. So they will be colored and the others won't be color. They will be colors. So first you have to, whenever you are getting this type of questions, write their electronic configurations. Okay, here scandium, vanadium, titanium and manganese is given, right? So here vanadium and manganese both are have partially filled d orbital. We have to write their electronic configuration and check whether they are having partially filled d orbitals. Okay, here the answer is vanadium and manganese ions. Next is scandium is a transition element but calcium is not. Why? So these type of questions are repeatedly asking one element as a transition element but the other is not. And why? What is the reason for that? Again, you know that transition elements, as I told you, and transition elements should contain some electrons in their d orbital. They should be partially filled also. Okay, so check, write their electronic configuration and check whether they have the partially filled d orbital in it. So here the answer is scandium having the electronic configuration with the incompletely filled d orbital, whereas calcium does not. So scandium is a transition element whereas calcium is not. Next question. Explain the following observation. Most of the transition metal ions exhibit characteristic colors in their aqueous solution. Or compounds of transition elements are often color. We are told that reason, right? Most of the transition elements complexes are colored because they are absorbing the radiation from the visible region and the electrons will be promoted from one of the d orbital to the another. So the ions of the transition element absorbing the radiation of a particular wavelength, and all the rest of these light will get, colors will get reflected and it will impart the color to the solution also. Okay, how would you account for the following? Most of the transition elements are known to form interstitial compounds. This also we have discussed while I'm taking class, right? So in the crystal lattice, transition elements have interstitial vacant spaces are there. So into which smaller sized non-metal atoms can be trapped. So these compounds are known as transition interstitial compounds. They are not ionic, they are not covalent in nature also. Okay, so they have a lot of spaces in there in which the smaller other atoms can be added. Next question. Which element in the first series of transition elements does not exhibit variable oxidation state and why? So the answer for this question is zinc. Zinc does not show variable oxidation state because it has completely filled the d orbital. As I told you, whatever that questions, all the properties of the transition elements are because they have the partially filled d orbital among them. Okay, partially filled. It should not be empty, or it should not be completely filled also. Here in this case, say zinc has an configuration with the 3D10 configuration, 3D10 for S2, so they are completely filled, so they won't show the variable oxidation state. Though a transition element scandium does not exhibit variable oxidation state. Reason. What will be the reason? Check their electronic configuration. Scandium does not exhibit variable oxidation state because it contains only 3 electrons in their valence shell, and after losing them it achieves a inert gas configuration. That is a inert gas configuration means it is become stable. Okay, write their electronic configuration 3D1 4s2. Their electronic configuration will be 3D1 4s2. So they have only 3 electrons in their valence shell. So if we are losing them, it will achieve the inert gas configuration. How would you account for the following? First question. Transition elements exhibit variable oxidation state. That question we have already discussed. Then the question is, transition metals and their compounds act as a catalyst, right? They are a very good catalyst. What's the reason for that? These metals, they are very good catalyst because they are showing variable oxidation state, so they can form unstable intermediate compounds, and it will provide a new pathway with the lower activation energy, and it has lot of vacant orbitals also, so they are very good catalyst. Okay, which metal in the first transition series, that is a 3D series, exhibit +1 oxidation state most frequently, and why? Okay, the 3D series, which is a metal which is exhibiting +1 oxidation state more frequently? There is only one answer for is copper. Cu plus ions is the only copper is the only metal in the first transition series which shows +1 oxidation state more frequently. It is because the electronic configuration of the copper is 3D10 4s1. When you write the electronic configuration, you can see that it will be 3D10 4s1. It will loses one electron and can form Cu plus 1 with the 3D10 configuration. Account for the following. The first question. Transition elements and their compounds act as a good catalyst, that we have discussed, right? Why they are acting as a good catalyst? They can form lot of intermediates with the lower activation energy. Moreover, they have vacant orbitals also, right? So the lowest oxide of the transition element is basic, whereas the highest is amphoteric or acidic. This part oxides, and this part is not the for your current syllabus, but still we cannot predict from which area the question will be asking, so we can just discuss it. The lowest oxide of transition element is basic, whereas the we know that metal oxides are basic, right? But when you go with the with the transition metals, we can say that it is becoming amphoteric, or even it is becoming acidic. What is the reason for that? Okay, the reason is that in the lower oxidation state, the transition metals behaves like a metal itself. So what will happen? All the metal oxides are basic in nature. Thus, in lower oxidation state, transition metals will be basic. But as oxidation state increases, its metallic character is getting decreased, right? We have studied that. Its metallic character is decreasing because of the decrease in their size. Thus, it becomes less metallic, or we can see that it's becoming more and more non-metallic. So oxides of a non-metal can be acidic, or it can even be amphoteric. That is why we are saying that in the higher oxidation state, transition metal oxides are amphoteric or acidic. Okay, so we are studying about the metallic bonding, right? The metallic bonding topic is thus, that is why I thought to say about this question also. But oxides, that topic is removed, but still we are studying about the metallic bonding. The reason for this question is their metallic bonding strength itself. We know that metals are basic in nature, but when the metallic bonding metallic properties getting decreased, they will be more tend to become acidic or amphoteric. That's the answer for this question. Second question is that transition metal exhibit higher oxidation states in oxides and fluorides. This question is coming from the part of an ionization energy. So ionization energy also we have discussed, right? So what is the reason for this? That is a transition element exhibit higher oxidation state in its oxides and the fluorides form. What is the reason for it? The reason is that when it is a fluoride, we know that it is a most electronegative element. So the transition elements shows highest oxidation state when it is in the fluoride form. The tendency of the fluorine is to stabilize in highest oxidation state because it has the highest lattice enthalpy also. So in the case of fluoride form, what will happen means transition elements are showing highest oxidation state because they have a more tendency to form lattice enthalpy. Okay, then ability of oxygen to stabilize this higher oxidation state, no, it will be more than that of the fluorine, because it is because of a tendency of oxygen to form multiple bonds. Oxygen has a tendency to form multiple bonds. That is why it is saying that transition elements are forming higher oxidation state when we check with the oxides or the fluorides form. So that is the reason for that. Fluoride, we know that both these elements, oxides, oxygen and the fluorine, they are very which electronegative. They are very electronegative in their nature, right? So that is why when it is bonded with the transition elements, so it is becoming that particular element is becoming more and more higher transition, higher oxidation state. So a transition metal is exhibiting higher oxidation state in oxides and fluorides form. Its only one reason is that is due to the higher electronegative nature of fluorine and oxygen. Both these elements are highly electronegative. That is why it is exhibiting higher oxidation state. Okay.